So here we go with quadratics, a new and important aspect of this course. There's quite a lot to go through today in this lesson, so let's go ahead and get started. So what's the big idea for this course is that we're moving from straight or linear functions relations to curved or quadratic relations. So let's contrast linear path with a quadratic path. So try to visualize the following situations. Walking at a constant speed across the room, or tossing an eraser up into the air and then catching it. So a couple of things for you to consider and fill into your document. How would you describe the difference between the two actions? So this is just based on what you visualize and what you know now. How would you describe the difference between these two situations? Then in the next part, try to decide which one of these situations represents linear movement or linear relationship, something that we've seen before. So remember in the last section, we talked about lines, linear systems. So remember that a linear function can be described using the equation y equals mx plus b. So in the equation of a linear function, the m is the slope, the b is the y-intercept. The slope of a line is how steep the line is, and on the graph you can see the slope and the y-intercept of a given linear equation. So the red line represents our line. The slope from a graph is determined by the rise over the run. In this case, if we count the rise, we get 8. And if we count the run, we get 16. So we get 8 over 16, and we reduce that, we get 1/2. So there's the slope. And then the y-intercept is where the line crosses the y-axis. So quick review of those things. We're going to move on. Let's just double check with some of these examples. Determine the slope and the y-intercept for each of these lines. Taking a quick look, we didn't quite extend it, but it looks right here that the y-intercept, or b, is right at -6. We want to find the slope of this line, then we're going to have to find a couple of points that link together right in the corners, because those are the easiest ways to determine the slope. So let's possibly use this point and this point. So we want to count the rise and the run, because the slope m is equal to the rise over the run on a graph. So if we take a look and we start at this point up at the top and we read from left to right, we have to come down 7 units. So that's going to make it -7. And then we count to the right 4 units. So the slope here, m, is -7 over 4. Taking a look at our next example. Here, we look for our y-intercept. Right here is the point where the line crosses the y-axis. This one takes a bit of an estimate. It looks here to me like b would be 2.5. And if we were to find the slope here, I think I would choose this point. And again, this point. Again, only because they lie right in the corners. So I'm going to draw in a triangle. This would be my rise and my run. Slope is rise over run, so we're going to count that now. And my rise is 1, 2, 3. And my run is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my slope is 3/10. Good. So quick review of linear relations. So let's start to introduce the quadratics. So a quadratic function is a nonlinear function. It can be written in standard form in the format of y equals ax plus bx plus c when a doesn't equal 0. This results in a U-shaped graph that's called a parabola, and it's the focus of the lesson, where b and c equal 0. So characteristics of quadratic functions. The lowest point on a parabola that opens up, or the highest point of a parabola that opens down, is called the vertex. And if you see on the graph, this parabola opens up, and the vertex is that point at which it changes direction. So this graph happens to be the graph of y equals x squared. That's our basic quadratic, our parent function. For this function, the vertex is at 0, 0. You can see that point right there. The vertical line that divides a parabola into two symmetric parts is called the axis of symmetry. And it's pointing there, but it's really pointing to this dotted line that runs through the middle of the parabola that cuts the parabola in similar halves, right? If you were to bend it in half or fold it in half, it would map onto each other. So the axis of symmetry, you can see it passes right through the vertex. So here, because our vertex is 0, 0, our axis of symmetry, which is always written as x equals, in this case, x equals 0. We can see that on the right side of the vertex, our graph is going up in a nice smooth curve. We say that this is increasing. And reading left to right, this side coming down here would be decreasing. So what happens is a quadratic has a section that's decreasing, gets to its vertex, turns around and changes its direction. So here what I want to do is I want to have you identify the vertex, the axis of symmetry, and the behavior of the graph at each of the ends. So taking a very close look here, the vertex is the point at which the parabola changes its direction. Here it looks like it occurs at 0, -2. The axis of symmetry is a line that passes through the vertex and cuts that parabola in half. And in this case, it looks like it's x equals 0. Then when we read the parabola or look at the parabola from left to right, we see that the parabola is decreasing here, reaches the vertex, and then goes to increasing on the other side. So just to fill in, our vertex is 0, -2. Our axis of symmetry is always written as x equals whatever the point is. In this case, it's 0. And then our end behavior, we will say it goes from decreasing to increasing. Let's talk about the domain of a function. So the domain of a function is the set of all the possible x values that the function can have, or all the possible x values that you can put into the function. The range of the function is the set of all the possible y values for the function. Now, for quadratics, the domain is all real numbers. And you can see it written as something like this. Sorry, that shouldn't be a y, that should be an x. So x is an element of all reals. Now the end behavior, y increases as x increases, can be written just like this. As x increases to positive infinity, y increases to positive infinity. As x increases to negative infinity, then y increases to positive infinity. Let's go back to our graph and take a quick look at this. So as x values go this way towards positive infinity, then the y values keep going up and up and up, and they move towards positive infinity. On the other side, as the x values move in the opposite direction towards negative infinity, getting more and more and more negative, then the y values are still going up. They are still moving towards positive infinity. So we use these infinity symbols in order to describe the end behavior of different types of graphs. So you'll see it throughout this unit when we talk about end behavior. The range is all real numbers greater than or equal to -2. Why do we say that? For here, we can see that the quadratic opens up and the lowest value that it reaches is -2. So if we consider x values horizontally here, that parabola is only going to come down to -2, and then it's going to extend up towards positive infinity. So we say here, we can write the range is y greater than or equal to -2. Okay, let's keep moving on. So let's talk about the vertex here. We can find the coordinates. Here's my vertex. It looks like it is 2, -3. My axis of symmetry goes right through the vertex. So here it looks like x equals 2. And we want to talk about the end behavior. So we are going to move from decreasing to increasing. And then the domain and range. So the domain, we can see, is any real number. X values that we can put into the function has no limitation. It can be any negative, any positive number. The axis of, the range, however, seems like it's bound on the bottom here. The y values for this function will never be lower than -3. So again, how do we write that? Domain, that is x, are all real numbers. But for the range, we have y is greater than or equal to -3. It'll never go below -3. Take a look at another one. Here we go with a parabola that's flipped upside down. The vertex is still the point at which the change in direction occurs. Here, it looks like it is -3, 7. The axis of symmetry is still the same thing. It goes right down through the vertex. And so here it looks like it is x equals -3. Now, because this parabola is flipped upside down, our end behavior looks like it's increasing, and then it switches to decreasing. There's still no limitation on any of the x values that you can sub into this function, so the domain here is still all real numbers. The range, however, this changes a little bit. Y has a maximum value here. It cannot be more than 7 because that parabola opens down. So y in this case has to be less than or equal to 7. All right, so we are going to, in this example, graph g of x, which is the function of g, is equal to 2x squared using a table of values and compare it to the parent graph of f of x equals x squared. I'm going to start here by putting in the parent graph, which is 0, 0, 1, 1, 2, 4. And this is the basic parabola of y equals x squared, this first function. So here is our basic shape of our function. And I'm going to change my color. So now we want to find some values of y equals, sorry, let's go g of x. And let's go 2 times 0 squared is still going to be 0. G at 1 is going to be 2 times 1 squared is going to be 2. G at 2 is going to be 2 times 2 squared, and it's going to be 8. And let's go the opposite direction and find g at negative 1. It's going to be 2 times negative 1 squared. It's going to be 2. And g at negative 2 is going to be 2 times negative 2 squared. Going to give me 8. So let me go ahead and plot these points. I'll write them into a table of values first. And we have negative 2, 8, and negative 1, 2. We have 0, 0, 1, 2, and 2, 8. So we still have 0, 0. We have 1, 2, 2, 7, 8. Takes me a little bit off my graph here. So this has a little bit of a change in the graph. We can see that the graph of 2x squared is a little thinner than our parent function, y equals x squared. So describe the difference between the graphs. We just talked about it. Okay, it seems that y equals 2x squared is, let's say, stretched. Vertically, because it has the appearance that you've taken it and you've pulled it, right, vertically, compared to the parent function of y equals x squared. So now we're going to take a look at a different function that's negative 1/2 x, and we'll build a table of values for that. But first, I'm going to go ahead and put my parent function down. So that's 0, 0, 1, 1, 2, 4. And you will get very familiar with these points of the parent function and something that should always be sort of memorized so that you can identify some key points in the parent function. Let's go to our table of values, and we will use the similar x values that we have in the parent function. So -2, -1, 0, 1, and 2. So let's plug those into our function and see what comes out. So g at -2 is going to be equal to -1/2 -2 squared. So -1/2 times 4, -2. Let's find g at -1 equals -1/2 times -1 squared equals -1/2. G at 0 is going to be -1/2 times 0 squared, which is going to be 0. G at 1 is going to be -1/2 times 1 squared, which is going to be -1/2. And then finally, g at 2 is going to give me -1/2 times 2 squared, and that's going to give me -2. It's a negative sign. So we're going to go ahead and plot these points. I'm going to zoom in just a little. So at -2, we have -2. At -1, we have -1/2, which is right about here. And at 0, we have 0. At +1, we have -1/2. At +2, we have -2. So if I go ahead and draw a smooth curve through these, you can see what happened. In this case, the parabola flipped upside down. It also seems to be a little wider than the parent function. So why don't you go right now and describe the difference between these two graphs? So it's flipped upside down, and it looks like it's wider. So wider, we would probably describe it as a vertical compression. So y equals -1/2 x squared vertically compressed, but also flipped upside down. And again, that's compared to the parent function, which is y equals x squared. All right, let's keep going. So here's the summary. When a is a negative value, then the graph of x squared is flipped upside down. 3 ways to spot a quadratic. First of all, you learn the first differences for a linear relationship, and if the first differences are all the same, then you have something linear. But for a quadratic, what happens is that the first differences are not the same. And so what we do is we check the second differences. And if the second differences come out to be the same, then you have a quadratic function. So if the second differences are constant, then the relation is quadratic. So that's one way to recognize a quadratic. If we just take a look at the equation, okay, a quadratic equation has to have a degree of 2. This means the highest exponent on a variable is 2. So something that would look like this in standard form. y equals ax squared plus bx plus c, we see that the highest degree, the highest exponent is 2. That's another way to recognize a quadratic function. And then by a graph, the shape of a quadratic is always a parabola. So if you see any shape like this parabola, whether it opens up or opens down, we know that we're talking about a quadratic function. So just wanted to talk about some terms that we'll see as they pertain to linear or quadratic functions and see what kind of differences there'll be. So for a linear function, we talk about the slope. But for a quadratic, we talk about a step pattern because it's not going to go up consistently and it's going to have a different step every time we move over one. It'll have a different value in the y direction. Linear terms, they usually have an x-intercept. In quadratic terms, we have zeros, and that's where the parabola crosses the x-axis. That can be at no points or at 1 point or 2 points, but we will see that in the next lesson. Then we have the y-intercepts. Both can have a y-intercept wherever the curve or the line crosses the x-axis. And then for quadratics, the new ideas is that we talk about a vertex and we talk about the axis of symmetry. So again, just to focus in on a bit of the differences here, the quadratic is on the left. We see we have a vertex. We do have a y-intercept. The vertex also happens to be on the x-axis, so it is an x-intercept and axis of symmetry. And then over on the right, we have a linear relation, linear function. It also has an x-intercept. It also has a y-intercept. And here our slope is rise over run. So why do we even care about x squared? Well, there's a lot of real world contexts where x squared or quadratic we can model and then we can help predict certain things. Things like gravity, the height of any falling object over time is quadratic. Business, if we want to see the most profit or the most revenue, that is also a quadratic function. Architecture, especially in the construction of bridges and satellite dishes. Again, those curves, parabolas, they are also quadratic. So if you can think of anything else in the real world around you, I want you to write it here. Anything else that makes you think of some kind of quadratic relationship. And then we want to take a quick look at these charts where we can find the first and second differences and determine if we are looking at a quadratic or something linear. So here we start with 15 minus 8 is 7. 24 minus 15 is 9. 35 minus 24, 11. 48 minus 35, 13. So our first differences are not the same, and so we're going to check our second differences, and we'll have 9 minus 7 equals 2. 11 minus 9 equals 2. 13 minus 9 equals 2. So our second differences are constant. So we're talking this chart represents a quadratic function. So we'll start here with B, first difference, 9 minus 5, that's 4. Then we'll have 13 minus 9, that is also 4. 17 minus 13 is 4. And 21 minus 17 is also 4. So we see here that our first differences are constant. There's no need to find our second difference. And this is a linear relationship. So we've done this before. I think I'm going to leave this with you to fill in. You need to just determine the slope and the y-intercept of these two linear graphs. And then in example 4, we're looking for the vertex, axis of symmetry, and x-intercepts. These graphs are all curves. They have that parabolic shape. And so we should be able to identify vertex, axis of symmetry, and x-intercepts. So I'm just going to do the first one with you and then leave you with the next ones. So the vertex happens right here. It's where the graph changes direction. And that vertex looks like it is at -2, 0. The axis of symmetry goes right through that vertex, and we write it as x equals, it goes through -2. And then finally, this graph looks like it touches the x-axis, touches this x-axis here at 0. So the x-intercept here equals 0. So I want you to go through and identify those 3 things for the last 3 graphs. Then finally, example 5. Remember, algebraically, if we're trying to find a linear or quadratic, that quadratic function has to have a degree of 2. So that's what we're looking for. So in the first one, y equals -2/3. We have x, but the degree on x is 1. When that's the case, we're talking about something linear. In the next one, we have y equals -2/3 x, but this time the degree is 3. Well, it's not 2, so this one is neither. It's not linear, and it's not quadratic. Y equals -x plus 6. There's an exponent here of 1, so that one is linear. Y equals 3x squared. There's our degree of 2. This one is quadratic. Y equals -x to the power of -1. -1. So we don't have a degree of 2 and we don't have a degree of 1, so this is also neither. It is not linear and it is not quadratic. And then at the end, y equals -2/3x squared minus 3, so there's our degree of 2. So this one is quadratic. So we can recognize quadratics algebraically as functions, graphically when we have a picture, if it's a line or a parabola, and then taking a look at this first and second differences. So that's it for this lesson. I knew it was a lot. Take some time to process it. Look at your homework for this lesson. If you have any questions, let me know, but we'll take some shorter chunks now as we go forward in Unit 2. So I'll see you soon.